Okay, so we were talking last time about the second fundamental form of a smooth map between Riemannian manifolds. So before talking more about that, let me just make one small comment, which is, so suppose you have E over M, a vector bundle, with a connection nabla on E. Then if I take any section S of E, this gives us a section nabla S of the bundle T star M tensor E. Let me explain how. So if I take a point P in M, then nabla S at the point P, this is a linear map from the tangent space to the manifold TPM to the fiber of the vector bundle E at P. What is this linear map? It's just V goes to the covariant derivative nabla sub V of S. Okay, so remember, any connection in the first variable, it can be localized to a point, right? That means the value of the connection, if I put in a vector field X here, then nabla X of S, this only depends on the value of X at the point P, right? Yes? Okay, so in the first variable, the connection can always be localized to a point. Therefore, this nabla sub V of S, this makes sense, right? This is nabla sub X of S at P, where X is any vector field whose value at P is equal to V. Is that clear?
Yes,
Yeah.
sir.
So what does that mean? That means that nabla S at each point P, it gives me a linear map from TPM to EP. So nabla S therefore defines a section of the bundle HOM TM to P, right? To E, sorry. Yes? Is that clear? And this bundle, the HOM bundle, as we've seen, I can write it as the dual of the first bundle tensor the second bundle, right? Yes? So this becomes a section of T star M tensor E. Is this clear?
Yes, sir.
Okay. So once I've got this nabla S, this is a section of T star M tensor E. I can think of this nabla S as sort of the first derivative of S, of the section S. And now I have an induced connection. I have a connection on T star M, which is the dual connection coming from the Levi-Civita connection on TM, right? So I have a connection on this tensor product bundle. So I can again apply that connection to this section nabla S, right? So then I can look at nabla squared S, right, which is nabla of nabla S, right? So where would this be? What bundle would this be a section of? You tell me, what would the bundle be? So each time I apply nabla, I pick up a factor of T star M, right? That's all. That means I get to act on one more tangent vector in M, right? So what would nabla squared S be a section of? Anyone? Yes, what would this be a section of?
T star M tensor T star M tensor E.
That's right. Yes, you just add in another factor of T star M, right? This would be a section of T star M, tensor T star M. Tensor E. Is this clear? Yes. Okay. And similarly, I can apply the covariant derivative K times. This would be the kth derivative of S, right? What would this be a section of? What would this be a section of? What was the bundle?
K times T star M tensor E.
Right. So the K-fold tensor product, right? Tensor E. Okay. And this is the same as what? This is the bundle of K multilinear maps, right? From Tm cross Tm K times to E. Is that clear? Yes.
Yes, sir.
Okay, this means multilinear maps, K multilinear maps from Tm cross Tm cross Tm K times to the bundle E. All right. Okay. So that's what this is. Okay. So example, if I take F as a map between manifolds, and I take V is a section of the pullback of the tangent bundle of N. Okay, so this is a vector field along F. So you should understand what these sections of the pullback bundle of the tangent bundle, what do these mean geometrically? This V is basically giving you, so you have your map F, right? So let's say it looks something like this. This is your map F. Right, so if I take a point P here, this goes to F of P. And now my V at P is what? A section of the pullback bundle means that VP is an element of TFPN, right? That's what it means to be a section of the pullback bundle. So that gives you a vector VP here, right? At the point FP in N. Is that clear?
Yes, sir.
So what that means is for every point in the domain, I'll have a vector at the image point. So this gives me a direction in which to deform F, right? So I'll take all points in the domain. Right, so those will map to some points in the range. So maybe this figure 8 curve maps twice onto this circle, right? And so then I'll get at each point. So if these 2 points map to the same point here, well, I'll get 2 tangent vectors, one this way, one this way maybe. Okay, so here I'll be deforming my map F so that it goes in this direction. Here I'll be deforming my map F so that the image moves in this direction. Okay. So the point is this vector field V along F, it gives you a way in which to deform F, right? Okay. And if your target manifold N is complete, right? even if it's not complete actually, well, if M is compact, then yeah, so okay, maybe I can state it this way. If N is complete or M is compact, then by an argument similar to what we did in a previous lemma, for any vector field V along F, there exists a variation Ft. So these are maps from M to N. For T small, such that, so this is a variation, means F0 is equal to F and del del T at T equal to 0. The variational vector field of this variation is equal to V. Okay. All right. So how do you get this variation? You simply put Ft of P to be the exponential map based at F of P in N applied to T times V of P. Is this clear? So if N is complete, then this exponential map is defined for all time, right? So this is well defined, okay? Otherwise, if N is not complete, but if you assume that M is compact, then this variational vector field V is bounded. So if it's bounded, then by compactness, you can cover N by finitely many small neighborhoods, such that on the image of each neighborhood, the exponential map is defined for a fixed time epsilon. And then if I take T small enough, then T times V, the norm of that is less than the epsilon where the exponential map is defined. And so then this is well defined. Okay. Is that clear?
Yes,
Yeah.
sir.
Okay, so these are the two cases we'll be looking at anyway. Usually we look at both manifolds compact. So then, of course, compact without boundaries. So then N is complete. So this makes sense. All right. Okay. So so every vector field along F occurs as the variational vector field of some variation of F. Okay. Is that clear? Yes?
Yes, sir.
Yes, sir.
Okay. So now if V is a section of F star Tn, then nabla V will be a section of what? Nabla V will be a section of T star M, right? Tensor F star Tn, right? Yes? Okay. And this is the same as a Hom of Tm F star Tn, right? Is that clear?
Yeah, it's clear.
Okay. And also, DF is a section of the same bundle. HOM TM F star TN, right? Okay. All right.
Yeah.
Okay. So now let us work out the first variation of energy. Okay, so let me recall the second fundamental form. This is nabla DF, right? So here DF is a section of this bundle. So this is T star M tensor F star Tn. So nabla DF would be just a section of the bundle given by tensoring with one more copy of T star M, right? So this is a section of T star M tensor T star M tensor F star Tn. So this is the same as the bundle of bilinear maps, right? Of Tm cross Tn to F star Tn, right? Yes. Okay. Yes.
Yes.
Yes, sir.
Okay. So nabla DF at P. This we saw was a bilinear map from TPM cross TPM to TFPN, which is the bilinear map VW goes to. So you first take the covariant derivative of the section DF in the direction of V. So DF is a section of the bundle of linear maps from Tm to F star Tn. So its covariant derivative in the direction of V, this will be a linear map, right? From Tm to F star Tn. So this will act on another vector W, right? This can act on another vector W and give you an element of TFPN, all right? So this is your bilinear map, and we showed that this is a symmetric bilinear map, right? We showed the symmetry of this last time using the symmetry of the Hessian of a function. Okay, so this is a symmetric bilinear map. So I should make a remark here, and this will be important for a computation we're going to do soon, that only the second derivative is symmetric. That means this nabla DF, it plays the role of the second derivative of F, right? Now, nabla DF is a section of a certain bundle, so I can apply nabla again to it, right? So I'll get nabla squared DF. That will be the third derivative of F, right? That will be a section of the bundle of trilinear maps from Tm cross Tm cross Tm to F star Tn, right? So similarly, I can look at the kth derivative. That will be nabla k minus 1 of df, right? That would be the kth derivative of f. But the point is only the second. So the kth derivative would give me a k multilinear map from the tangent space cross itself k times to the bundle f star Tn, all right? But it turns out in general, only the second derivative is a symmetric multilinear map. All the higher derivatives for maps within Riemannian manifolds, unlike the Euclidean situation, for higher derivatives, they are no longer symmetric multilinear maps. if you interchange two vectors, what happens is actually some curvature terms come out. Okay, so we'll see that. We will be looking at the third derivative in a while when we prove what's called the Weizenbach formula. So actually there some third derivatives will come up, and there you'll see if you interchange the orders of vectors, you'll get some curvature terms coming out. Okay. So this is a difference from the Euclidean setup. In the Euclidean setup, we saw that all the derivatives were symmetric multilinear maps, right? Yes? Okay.
Yeah. There
So
the curvature is zero, so
correct. The curvature is zero. That's correct. The curvature is zero. So you don't see the curvature terms when you look at higher derivatives. So yeah. But in the Riemannian setting, only the second up to the second derivative is symmetric. All higher derivatives in general are not symmetric. Okay. Anyway, so for a symmetric bilinear map, we can define its trace, right? So this defined for us the tension field tau f at a point P. This was defined to be the trace of nabla df at P. And this trace for a symmetric bilinear map, taking values in a vector space, the trace is defined as the sum over any orthonormal basis of the symmetric bilinear map applied to EI, EI. Okay. EI is any. So we showed that this was well defined independent of the choice of orthonormal basis, right? Yes. And so this I can write as sum over I nabla EI df applied to EI. Okay. So this is the tension field of, so this is an element of what? This is at each point, this is an element of TFPN, right? So this tension field tau f, this is a section of the bundle F star Tn, right? Is this clear?
Yes, sir.
Okay. So now let's come to the first variation of energy. Okay. For okay, for a variation of a smooth map F. So FT is a one parameter family of smooth maps. So F0 is equal to F. And we have the variational vector field V is equal to del del T at T equal to 0 of FT. So this is a vector field along F. So this is a section of F star Tn. Okay. Now let's do one small calculation. So suppose I take a point P and I take a tangent vector V at P. So what I can do is I can choose a curve gamma so that V is equal to gamma prime 0, okay, in TPM. and this P is equal to gamma 0, right? Okay. So then what I can do is I can look at the images of these curves under the maps FT, the image of this curve under all the maps FT. So that will give me a one parameter family of curves like this, right? So say this point is f of P, and then this is F composed with gamma, and this is say FT composed with gamma. So this perpendicular curve is when I move in the T direction. It may not be perpendicular. I'm just drawing it to be perpendicular. So this point here would be say FT of P. Okay. And in general, what you have here, you've got a parametrized surface, right? So a point here or a point here, let's say, would be of the form Ft of gamma of S. Okay. All right. Yeah. So if I look at dft of V, this is what? This will be a tangent vector at Ft of P, right? Yes. Okay.
Yes.
So this T goes to dft of V. This is a section of Tn along the curve T goes to Ft of P, right? It's a section along a curve. Yeah, is that clear?
Yes.
Okay. So I can compute its covariant derivative. Okay. So what is d del T at T equal to 0 of dft of V? So this is equal to, now dft of V is equal to gamma prime 0, right? So by the chain rule, dft of V I can write as del S at S equal to 0 of Ft of gamma S, right? This is by the chain rule. Yeah. And then outside I have this d del T at T equal to 0, right? Yes. This is just by the chain rule. Is this clear?
Yes, sir. Right.
When I differentiate in S, what will I get? I'll get dft at the point P applied to gamma prime 0, right? Which is V, right?
Yeah.
Now, this is a parametrized surface, this Ft of gamma S, right? This parametrized surface. So I know for a parametrized surface that by symmetry of the connection, I can interchange d del T and del S, right? So this will become d del S at S equal to 0 of del T at T equal to 0 of Ft of gamma S, right? Yes.
Yes, yes.
So now what is del T at T equal to 0 of Ft of gamma S? That is nothing but V of gamma S, right? Right. That by definition is my variational vector field V, right? So this becomes d del S at S equal to 0 of V of gamma S. This, by the property of the covariant derivative, the compatibility with the connection, this is nothing but nabla sub V of capital V. Is that clear?
Yes, sir.
Okay. So where does this belong? This belongs to TFPN. Okay. All right. So thus, if I look at the covariant derivative, if I look at this linear map, so, okay, let me write it like this. So d del t at t equal to 0 of dft, right? So this I can think of as a linear map. So V in should I put it? Yeah. So V in Tm goes to d del t at t equal to 0 of dftv. Okay, this is a linear map, right? This is in f star Tn. This linear map is the same as the linear map V in Tm goes to nabla sub little v of capital V, right? Okay. So therefore, this is equal to the section nabla sub V. Okay. Is that clear? Which is a section of T star M tensor F star Tn. All right. Is this clear?
Yes, it's clear.
Okay. Okay, so there's less than a minute. So let me stop this session and start another one. We'll finish the computation of the first variation of energy. Okay. 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 So now what I'm going to do is find a vector field. So at a point P, right, V at P belongs to TFPN, and if I look at DF at P, so this is a linear map from TPM to TFPN. So I can look at its adjoint, since those are inner product spaces. The adjoint goes in the opposite direction from TFPN to TPM. So I can look at I can define a vector field on M. X at P is what? This is defined to be dF star at P applied to V at P. So this is an element of TPM, right? Okay, so X is a vector field on M then. Yes? Okay. Is this all right? Yeah.
Yeah.
So if I let EI be an orthonormal basis of TPM, then what is the divergence of X at P? So we saw this is equal to the trace of the covariant derivative of X, right? Nabla X at P, right? We prove this, yes? Yes?
Yes, sir. Yes.
Yes, yes.
Okay. So what is the trace? Trace means the sum over I, the ith diagonal entry of this linear map with respect to the orthonormal basis EI. So what is the diagonal entry? It is the linear map applied to EI, inner product with EI, right? So this is sum over I, inner product, nabla EIX, inner product EI, right? Yes.
Yes, yes.
Now, what is X? X is equal to df star of V, right? Yes. So now, by the rules for covariant differentiation that we did last time, this df star applied to V, differentiating this satisfies a Leibniz rule. This is going to be nabla EI of df star applied to V plus df star applied to nabla EI of V, right? Inner product with EI. Yes.
So this is from the formula satisfied by a section of
Yeah,
E star tensor F, like that.
correct. So let me just write that this follows from, follows from nabla X of beta of S is equal to nabla X beta applied to S plus beta applied to nabla X S. So this is a section of the bundle F where beta is a section of E star tensor F and S is a section of E and X is a vector field on N. We proved this last time, right? Yes? Yes?
Yes, sir.
Okay. Now, this nabla EI df star, this is a linear map from TPM to TFPN. So we showed that this linear map, well, sorry, it's in the opposite direction. From TFPN to TPM, we showed that this linear map, this is the dual of the linear map, nabla EI df, right? So this is nabla EI df whole star applied to V. Right? We showed this equality last time. Yes? Yes?
Yes, sir.
Okay. So now I've got two adjoints, so I can move them to the right-hand side, right? By definition of the adjoint for a map between inner product spaces. So this becomes inner product of V with nabla EI df applied to EI plus I'll get another term sum over I inner product of nabla EIV with df of EI. Okay. Now the first term, this V is fixed. I can take the sum inside the inner product. So then the first term becomes what? The inner product of V with this sum over I, nabla EI dF of EI. This is nothing but the tension field of F, right? Yes? So the first term becomes inner product of V with the tension field of F. Is that clear?
Yeah, it's clear.
Yes, sir.
And what is the second term? The second term is nothing but the inner product on the bundle of linear maps, right? From Tm to F star Tn, right? So this is the inner product between the linear map nabla V and the linear map dF, right? Is that clear?
Yes,
This
sir.
nabla V applied to EI, and this is dF applied to EI. You take the inner product and sum over I. This is nothing but the trace of dF star nabla V, right? Which is the inner product between nabla V and dF, right? Is that clear?
Yeah, it's clear.
Okay. So this thing, so thus what we get is, so thus this thing is a divergence. Okay, so the divergence of X is this sum. Okay. All right. So now we can compute the.
I just have one question.
Yes, yes.
Why is covariant derivative of del nabla EI dF star is equal to star of nabla EI dF? Why?
We proved that last time. We proved that last time. We
Okay.
proved that last time. Yeah. So if you look through the notes for last time, we proved it last time. Yeah.
Okay.
Yeah, we proved that last time. Yeah. All right. Okay. So now we can compute the first variation of energy. So ddt at t equal to 0 of energy of Ft. So this is ddt at t equal to 0 of half the integral over m of the inner product of df with df, right? d vol m. Okay. So by the metric compatibility, this is going to be half. I can take the differentiation inside the integral sign. So dft. Okay. So then I'll get basically the inner product of the covariant derivative of dft with respect to t. Inner product with df, t at time t equal to 0. So, and then twice that, right? So the twice and the half will cancel. So this will become integral over m of d del t at t equal to 0 of dft, inner product with dft at t equal to 0 d vol m. Okay. Now, we computed this covariant derivative, d del t of dft. This we saw was equal to nabla v, right? Yes, this was nabla v. And this dft at t equal to 0, this is just df, right? All right.
Yes, sir.
So now we can use this formula for the divergence of the vector field x that we had, right? What will this be? This inner product of nabla v with df, this is going to be divergence x minus this inner product of v with tau f. So this becomes integral over m divergence of x minus inner product v with tau f. Okay, the whole thing d vol. Okay, now we assume that Well, we can assume one of two things. Either we can assume that the boundary of M, the domain is empty, or we can assume that if the boundary is non-empty, then all the maps FT are constant on the boundary of M. Okay. So either way, that will give us that the vector field X, if the boundary of M is non-empty, it vanishes on the boundary of M, or otherwise the boundary of M is empty. In that case, when you integrate the divergence, you'll get 0 by the divergence theorem. So either way, this divergence vanishes. The integral of the divergence vanishes, okay, by the divergence theorem. So you just get minus the integral over M of V inner product tau F d vol M. Okay, so by the divergence theorem. So for simplicity, let's assume that this is the case we'll be looking at in most of the course. Boundary M is empty. Okay. Is this clear?
Yeah, it's clear.
Yeah. So thus what do we get? Thus we get that so this is the first variation of energy. Okay. This is minus the integral over M of the inner product of V with the tension field of F. Okay. So what do we get? What happens if you have a map which is a critical point of the energy functional? So what does it mean to be a critical point of the energy functional? That just means that the first variation of energy is 0 for all variations Ft of F. This happens if and only if the integral over N of the inner product of V with tau F d vol M, this is 0 for all sections V of the pullback bundle F star Tn, right? And this happens, it's easy to see. So since tau F is a smooth section of this pullback bundle, I can take V equal to tau F. So then I'll get the integral of norm tau F squared equal to 0. That means that tau F is identically 0, right? So this happens if and only if tau F is identically 0. Is this clear?
Yes, sir.
Okay. So by analogy with the case of closed curves and geodesic and functions, we saw that those were critical points of the energy if and only if the curve was a geodesic or the function was a harmonic function. So for a harmonic function, that meant the trace of the Hessian is 0. Here, what we're getting is that this vector value trace, the trace of the second fundamental form is 0, right? And so we now take this as a definition of a harmonic map. So definition of a harmonic map. So F, a map between Riemannian manifolds is a harmonic map if its tension field is identically zero. Okay. So is this clear?
Yes, sir.
Yeah. So for example, if gamma is a curve in M, okay, what is nabla d gamma? Okay, maybe I should. So what is d gamma? D gamma let me just do this out explicitly. So d gamma at t is the linear map from R to t gamma t m. H goes to H times gamma prime t. Okay, this is d gamma at t. Right. Okay, so actually, well, let me. Okay, yeah, this is okay, fine. So before doing this example, let me just do some little a computation about the second fundamental form. Okay. So maybe that will make it simpler. Yeah. Let me do that first. Okay, so we have the second fundamental form. Nabla df at P. This is a symmetric bilinear map. So because it's symmetric, it is therefore determined by the quadratic map where you restrict the bilinear map to the diagonal, right? Any symmetric bilinear map will be determined by the quadratic map, right? QP from TPM to TFPN. V goes to nabla DFP of V comma V. So it's not a quadratic form because it's vector valued. It's a quadratic map, okay? That means if I choose bases, then the coordinates of this will be quadratic polynomials in the coordinates. Okay. So it's a quadratic map. Anyway, what the point is that we just need to compute the second fundamental form along the diagonal, right? Along v comma v, right? So this second fundamental form along the diagonal, this has a very simple geometric interpretation. Okay, so I have f from m to n, right? And let me take gamma is a curve in M, okay? So let me take phi equal to x1 to xn. Local coordinates on M. And let me take phi composed gamma of t. This is going to be given by functions x1 of t up to xn of t. Okay, so then as we've seen before, that gamma prime t, I can write as the sum over I, xi prime t, del del xi, right? At gamma t. Yes? Okay. So if I look at the covariant derivative ddt of gamma prime, then by the rules for the covariant derivative, this is going to be by the Leibniz rule, it will be sum over I xi double prime into del del xi, right? Plus I'll take xi prime, and then I have to differentiate this del del xi at the point gamma t. But del del xi is a section of the tangent bundle on an open set in M. So when I restrict that to the curve and I take the covariant derivative along the curve, by compatibility of the covariant derivative with the connection, this is just nabla sub gamma prime of del del xi, right? Okay. Fine.
Yes, sir.
Okay. Now, let me look at F composed with gamma. Okay. So, F composed with gamma is a smooth curve in N. So if I look at its derivative by the chain rule, this is df at the point gamma applied to gamma prime, right? Now df applied to gamma prime by linearity, this will give me what? This will be sum over I xi prime df of del del xi, right? df at gamma of del del xi, right? Okay. Yes. So now let me look at the covariant derivative of F composed with gamma. So ddt of F composed gamma prime, what will this be? So I just so this df at gamma applied to del del xi, I can write this as df of del del xi. This is a section of the pullback bundle f star tn, this composed with gamma, right? I can write it like this. Okay. Yes. So now when I take the covariant derivative of F composed gamma prime, so I'll get one term which is sum over I xi double prime df of del del xi composed with gamma plus, now what do I have? I'll get xi prime into, so here I have a section of the pullback bundle, right? So df of, let me write out what this is. df of del del xi, this is a local section of the pullback bundle, right? F star Tn, where this U is an open set in M. It's the domain of the chart X1 to Xn, right? This phi goes from U to Rn. Okay. Is this clear? Yes?
Yes,
df
sir.
del del xi is a section of this pullback bundle. So now, when I differentiate this section of the pullback bundle restricted to the curve, when I take the covariant derivative, right, what will that be? That by the definition of covariant derivative of a section along a curve, that is going to be nabla sub gamma prime of df of del del xi. All right. Okay. Now I can use the property that we proved earlier, that when I have a section of a bundle of the form E star tensor F, right? Where was that property? Here, this property, right? Nabla x of beta of S is nabla x beta at S applied to S plus beta of nabla xs. So here, this is true for all vector fields X, right? At all points. So I know that this covariant derivative, all of these covariant derivatives only depend on the value of X at the point P, right? So I can replace this. This is true for any tangent vector V at a point P and M, right? Okay. So over here, yeah. So over here, I can apply that property. I'll get a Leibniz rule for this derivative of df composed with del del xi, right? So what will I have? I'll have, so sum over I xi double prime df of del del xi composed with gamma plus xi prime. So I'll get one term which is nabla gamma prime df right applied to del del xi, plus I'll get another term xi prime df of nabla gamma prime of del del xi, right? Okay. So now I can put these terms together as follows. This term here, what is this? This xi prime I can put inside. And so then this, when I sum over, I'll get basically nabla gamma prime df. I put this xi prime inside and I sum over I, right? So inside, what will I have? Sum over I xi prime del del xi, right? Yes. This thing is nothing but my gamma prime again. All right. And then I have, here I can take this df, I can put this xi double prime inside the df. And here I put this xi prime inside the df. So what I'll get is df of inside, I'll get sum over I xi double prime del del xi plus xi prime nabla gamma prime of del del xi, right? Okay. Now this term, this sum that we computed earlier, this is equal to ddt of gamma prime, right? Is this clear? Yeah, so what are we getting? Finally, this becomes equal to nabla gamma prime df applied to gamma prime plus df applied to d gamma prime dt. Is this clear? Yes?
Yes, sir.
Okay, so what is this? This is nabla df applied to gamma prime comma gamma prime, right? Plus df applied to d gamma prime dt. Okay, so let's write gamma double prime for d gamma prime dt, okay? For any curve gamma in a Riemannian manifold. Okay, then what we've proved is, what were we computing here? We were computing the covariant derivative of f composed gamma prime. So this is f composed gamma double prime, right? So we've got a formula for the the second derivative of the composition f composed gamma double prime. This is equal to the second fundamental form nabla df applied to gamma prime comma gamma prime plus df applied to gamma double prime. Is this clear? Okay. Yes, this is what we proved. Is this clear?
Yes, sir.
Okay. So we've got a formula for the second derivative of a composition, okay, of a map with a curve. So this gives us the value of this nabla df, the second fundamental form along the diagonal, right? Because thus if V is a vector in TPM and gamma is a geodesic in M such that gamma 0 is P, gamma prime 0 is V. So what in this composition formula, if gamma is a geodesic, then gamma double prime is 0, right? So this second term vanishes. So then you get just the second fundamental form applied to the diagonal, right? So then we can compute the second fundamental form. Nabla df applied to V comma V is what? This is nothing but f composed with gamma double prime 0. If gamma is a geodesic. This is only true for a geodesic because then this second term vanishes. Okay. Is this clear? Yeah.
Yes,
So
sir.
this should remind you of the formula we proved for maps in Euclidean space. that the second derivative applied to v comma v was just the second derivative of the map f restricted to a straight line p plus tv. The point is, a straight line is a geodesic in Euclidean space. Okay. And here you have the same analog of that formula, that if you take a geodesic in the manifold M, then you look at the composition of f with that geodesic, take its second derivative, the covariant derivative. So that will give you the second fundamental form applied to v comma v. Okay. All right, so let me stop this and start a new session. Okay, I'll just be back in 2 minutes. All right, so we have this formula which.
So this holds true for the Hessian as well, right? I mean, so in
Correct,
replacing the
correct.
second fundamental.
That's right. So we proved this for the Hessian, if you recall, right? That the Hessian you can also compute as the second derivative along a geodesic, right? So the important point is that the curve you take has to be a geodesic so that this second term vanishes with gamma double prime. Okay. This is not true for any curve. The curve has to be a geodesic. Okay. Is it clear? Yeah, so that the second derivative of the curve is 0. The acceleration of the curve has to be 0. All right. Yeah.
Yeah, it's clear. Yeah.
It's clear. Okay. So this tells us a few things. So well, we can work out using this. We can work out a composition formula for the second fundamental form of a composition of two maps. Okay. We can do that. Let me not do that right now. We'll do that later anyway. So, no, what I want to do now is the following. So, let me make a definition. Of what are called maps which are totally geodesic. Okay. So, F is a smooth map between Riemannian manifolds. I'm not writing that. So we say that F is totally geodesic at P if the second fundamental form at P is identically 0. Okay. And we say that F is totally geodesic, a totally geodesic map, if it is totally geodesic at all points. So nabla DFP is 0 for all P and N. Okay. So let me give you some examples. So examples. One, if F is an isometry, so that means that F is a diffeomorphism. such that it preserves inner product. So inner product DFP V DFP W is equal to inner product VW for all VW in TPM, P and M. So then you can show then gamma geodesic implies F composed gamma. So gamma geodesic in N if and only if F composed gamma is a geodesic in N. Okay. And so nabla DF of VV, this is equal to F composed gamma double prime 0, where gamma is a geodesic such that gamma prime 0 equal to V, and this is equal to 0 because F composed gamma is a geodesic in N. So that implies that F is totally geodesic. Its second fundamental form vanishes identically. So any isometry is totally geodesic. Okay. All right. Is this okay?
Yes, sir.
So what's another example of a map which is maybe not totally geodesic everywhere, but totally geodesic at a point? If I look at the exponential map at B, so this is going from TPM to M, right? This actually is going to be totally geodesic at the origin, because geodesics in TPM passing through 0 are just straight lines, right? TPM is just a vector space, inner product space, right? So geodesics in it's isometric to Rn, right? So geodesics are just straight lines. Okay. So geodesics passing through the origin are just straight lines. Gamma of T equal to TV, right? And so nabla DF at the origin of V comma V this is F composed gamma double prime of 0. This is 0 because F composed gamma of T, this is what? This is just X of TV. This we've already seen is a geodesic, right? In N. Is this clear?
Yes, sir.
But notice we can only say that the second fundamental form of the exponential map at the origin is 0. I can't say it at any other points. Because at another point, the geodesic passing through a point W will be of the form W plus TV, right? And I don't know that exponential of W plus TV is a geodesic. That I don't know. I only know that the exponential of TV is a geodesic. Is that clear? Yes?
Yes. Yes.
Okay. So I can say, therefore, the exponential map is totally geodesic at the origin. Okay. Now, this we can use to prove something I was mentioning last time, that the tension field I can compute as a Laplacian of a vector valued function. So first of all, if V is a finite dimensional vector space over R, of course, and F is a map from a smooth manifold, Riemannian manifold, into V. M is a Riemannian manifold. Yeah. Then we can define the Laplacian of F as a vector valued function, as a V valued function, right? So okay, so, well, okay, yeah, I don't, yeah. Okay, then Laplacian of F, this is a smooth map from M to V, is defined by the property that Laplacian of alpha composed F is equal to alpha composed Laplacian F for all alpha in V star. Okay, so see, Laplacian F is at a point P is going to be a vector in V. To tell you what a vector in V is, you just need to know what is the image of that vector under all dual elements, right? How do dual elements act on that vector?
Right.
So telling you what the action is, alpha acting on the vector Laplacian F is equal to the Laplacian of the scalar function alpha composed with F. Okay. So it's easy to see that this is well defined. Okay. Because I mean, you choose a isomorphism of V with Rn. Okay, so see, if F is equal to F1 to Fn, or say Fm from M to R to the M, then Laplacian F is simply the vector Laplacian F1 up to Laplacian Fm. Okay. Is this clear? Yes?
Yes, sir.
Okay. Fine. So, now I want to consider F a map from M to N. And I have say an open set U in M, which maps into, so this is P, this is F of P, and this is a, say, a geodesic ball around F of P. So on this, I have by definition the inverse of the exponential map, X sub Fp inverse, which you can call a logarithm if you want. It's the inverse of the exponential. So this maps into a ball, say B tilde, in the tangent space at Fp. Okay. All right. So we have this picture locally. Yes. Right. So then I get a, locally I get a map F tilde. Right. So I have F tilde. This is X Fp inverse composed with F. Right. From an open set in M, a neighborhood of P, mapping into a ball in the tangent space to Fp. So mapping into a vector space, right? So let me do this. This is mapping into a vector space. Okay. So let's call H is this map. X Fp. So this is going from a ball in the tangent space around 0 to a ball around F of P in N. Okay. So then I can write F as H composed with F tilde, right? Okay. And we know that H is totally geodesic. At 0 in TFP N. Okay. So um, gamma is a geodesic in M such that gamma 0 is equal to P, and I let gamma tilde be F tilde composed with gamma. Okay. Right. Then F composed with gamma. This is what? This is H composed with F tilde composed with gamma. So F tilde composed with gamma, I'm calling gamma tilde, right? Okay. Yeah. So just 1 second, I have to take this call. Sorry. Okay, sorry. Yeah, so all right. So okay, so right. So if since gamma is a geodesic, so then what do I get? I get that nabla df so let's suppose gamma prime 0 is V in TPM. Right. So then by what we proved earlier, this is equal to, since gamma is a geodesic, this is equal to F composed gamma double prime of 0, right? But this is equal to H composed gamma tilde double prime of 0. But now this we know is equal to nabla dH of at 0 of gamma tilde prime 0 gamma tilde prime 0 plus dH at 0 of gamma tilde prime 0 gamma tilde double prime 0, right? Okay. Yes, but H is totally geodesic at the origin, so this first term is 0, right? Is this clear?
Yes, sir.
And this H is the exponential map, so the derivative of H at the origin is identity, right? Yes. Okay. The derivative of the exponential at the origin is the identity, right? We've seen that. So what do we get? This becomes just gamma tilde double prime of 0. Okay. And what was gamma tilde? It was F tilde composed with gamma. So this becomes F tilde composed with gamma double prime of 0. Okay. So so now let EI be an orthonormal basis of TPM and let gamma I be geodesics such that gamma I prime 0 is equal to EI. Okay, then we can compute the tension field tau F at the point P. This is what? This is equal to sum over I nabla df of EI comma EI, right? But this, as we've just seen, this is going to be equal to sum over I F tilde composed with gamma I double prime of 0, right? Yes. And this, if you think about it, this is nothing but the Laplacian in N of F tilde at the point P, at the point F of P. So, where is this going to be? No, at the point P. This is the Laplacian of N, sorry. This is the Laplacian of N, sorry. F tilde is defined on M. So F tilde is the log composed with F, right? So, okay, so you have F. And this is your map F tilde, right? So you can think of this as log sub FP of F, right? Okay. So what you get is that this is the Laplacian of log F at the point P. This is the usual Laplacian of a vector valued function, right? Okay, so I should have said this Laplacian of a vector valued function, right? What is this? This Laplacian of a vector valued function, say taking values in Rn, right? What is this? This is each component is sum over I this is F1 composed with gamma I double prime 0, right? Up to Fm composed with gamma I double prime 0, right? Where gamma is a geodesics whose tangent vectors at P are equal to an orthonormal basis, right? Is this clear? Yes. This is from the definition of the Laplacian, right? It's trace of the Hessian, and the Hessian is given by these second derivatives along geodesics. Yes. Okay. So this is nothing but, I can take the sum outside the vector. So this is sum over I, F composed with gamma I double prime 0. So this is an element of Rm. Is this clear? Yes? Okay.
Yes, sir.
Yeah, so what are we getting? We're getting that this tension field I can write as a Laplacian of a vector valued function at the point P. This is not true at other points in this neighborhood of P. This is only true at the point P. Because here we use that the exponential map, this is totally geodesic at the origin. Okay. is this clear? See, the point of this is that what this shows you is that to define the tension field, you don't actually have to go through the whole machinery of induced connections on dual bundles and tensor product bundles and so on in order to define the second fundamental form of a map and so on. You just need the Levi-Civita connection on M and the exponential map of N. That also depends just on the Levi-Civita connections, right? All you're doing is this Laplacian of F tilde. This is the Laplacian of N applied to F tilde. This only depends on the Hessian, right? Of the coordinates of F tilde. And the Hessian is defined, we know how the Hessian is defined, right? By just taking the Levi-Civita connection applied to the gradient vector field, right? Okay. So, so if you like, this gives a simpler way to compute the tension field. Okay. Does this make sense?
Yes, sir.
Yes.
Yes, sir.
Any questions? So it shows you that the tension field is a sort of nonlinear Laplacian, right? It's a nonlinear operator, but it's given by, see, the nonlinearity is contained in this log f, right? So first you take log f so that f becomes a vector valued function, right? F tilde, and then you take the Laplacian of a vector valued function, right? So your target space is, normally it's curved, you're making the target space flat by using the inverse of the exponential. Then for a map into a vector space, you can just take the usual Laplacian. You understand?
Yes. Right.
That's the point. So, okay. Okay, so to finish, maybe I should just say a bit more about totally geodesic maps. Something I forgot to say. So here's a little proposition, which I'll just quickly, well, the proof is just a couple of lines. So here is F smooth map between Riemannian manifolds, and P is a point. So P is a point in M. So then F is totally geodesic at P. If and only if F composed gamma double prime 0 is equal to 0 for all geodesics gamma such that gamma 0 equal to P. And 2, F is totally geodesic as a map from M to M. So that means the second fundamental form vanishes at all points P, if and only if for all geodesics gamma in M, F composed gamma is a geodesic in N. So F is totally geodesic if and only if it maps geodesics to geodesics. That's why, hence the name totally geodesic, because it maps geodesics to geodesics. Okay. So the proof of one is clear, right? So that nabla DFP VV this is equal to F composed gamma double prime 0 for gamma geodesic such that gamma prime 0 equal to V. So this implies 1, right? Yes? Is that clear?
Yes, sir.
Yeah, nabla DFP is going to be 0 if and only if this F composed gamma double prime is 0 for all geodesics. Gamma such that gamma 0 is P. And then part 2 follows from part 1, right? So nabla DFP equal to 0 for all P, right? This is if and only if F composed gamma double prime T equal to 0 for all T for all geodesics gamma in M, right? Yes?
Yes.
Okay, because F composed gamma double prime of T is equal to nabla DF at gamma T of gamma prime T. Gamma prime T. Okay.
Yes.
So that's it. So F composed gamma double prime equal to 0 means that F composed gamma is a geodesic, right? So that's it. Okay, so this is if and only if F maps geodesics to geodesics. Okay. Okay, fine. So let's stop here today and we'll continue on Friday. Okay. So you just send me an email confirming about the end sem exam being conducted via presentations. Okay. All right.
Yes, sir, I will ask for associate today and.
Yeah. You confirm with everyone and you get back to me. Okay.
Okay, sure.
Yeah. Okay. Thank you. Okay.